Okay, good morning. Are there any questions before I start? Yes.
This is the problem set 8, question 4.
Yeah.
So, how do we need to find the displacement factor D? Because we are not given hardware efficiency.
Problem 4. Problem 4. And what are you asking?
So, we are not given hardware efficiency.
Yeah.
So, S transpose and P transpose we can find out by the space-time graph and drawing the space-time table.
Well, I mean, you say that you are not given hardware utilization efficiency, but I already mentioned here, replace each delay by 2 delays. That means it's interleaved by factor 2, which means hardware utilization efficiency is 50%, assuming there is only one time series. For now, we can assume. So is that enough or? Okay. Okay. All right. Any other questions? Okay. If not, last time we were talking about adders, binary adders and multipliers, and I started talking about representation in 2's complement numbers, and then we talked about fast adders. Fast adders, 2 types of fast adders, the carry select adders and the carry look ahead adders. And then we talked about multipliers, and we talked about the carry ripple multiplier, then we talked about carry save multiplier, and then we talked about Baguli multiplier, which does not require extending the sign bit. Okay, so we talked about all of that, and I proved one particular table from the book, and then I didn't talk about this, but I handed out in your lecture notes that there is another way to simplify the arithmetic as well, and the main difference between the so-called this table and the other table is that the complement here is first and then complement A2, B3 and the complement of that whole thing. But here we have A2 bar B3, so the complement is not over the whole thing, just over one bit. So that's the main difference. And there are problems in the textbook that ask you to derive these, and there are hints given, and if you follow those hints, you should be able to get to that table. Okay. So today I'm going to talk about, so let's talk about what modified Booth recording does. Okay, how many of you have heard of Booth recording or modified Booth recording? Anyone? I'm sure you have heard of it or not. Raise your hand if you already have come across modified Booth recording in some kind of class on logic design or VLSI design, or maybe 4301, something like that. Anybody here? Okay. So let's say that let's say I have a number, let's say word length is 8 bits, and let's have a number A, which is A7 point, A6, A5 through A0. Okay, so we have an 8-bit number represented by this. A7 is the sign bit or the MSB, and then the radix point, and then all these LSBs. LSB is A0. Okay. This is the MSB or sign bit. If A7 is 1, that's a negative number. That's why the weight is -1. Okay. Well, so if I want to multiply A times B. Okay, so A times B, and we talked about that briefly. Well, we saw at least one way of doing that by the Horner's multiplication. Okay. So we saw that if I am going to compute A times B, then we can express this whole product using Horner's rule, and using Horner's rule we can have a table like that. Okay, so if we think about, let's think about this now. For now, let's think about this table here. So so in this particular example, we have this. If I do, let's assume that B is well, B doesn't really have to be they don't have to be of same word length, so they could be a different word length. So let me say that B, well, it doesn't matter. B is 8 bits. Okay, so B also is 8 bits. So then we can see from this. So if I just follow the example from before. So we start with A times B 0, and then scale that by factor 2 to the power minus 1. So if I take A7 B 0 all the way up to A0 B 0, and then this is A1 B 0, and scaling that means throwing this away and sign extending A7 B 0. So that's kind of 2 to the power minus 1 AB 0. So I don't want to write all this, but let me put just dots. You have to relate, when I put these dots, you have to relate 3 plus 2 5 plus 3 8. Okay, so these are the 8 bits. Okay, I'm not going to write a lot these things. So so that's A times B 0, and then take that out and sign extend. So that's so I put these dots so you know what I'm doing. Okay, so the next one is A times B 1. So we put these dots. Okay, and we add them, and then so I have something here that I throw out. So that's the first partial sum. This corresponds to A times B 1, and that's scaled already, and then A times B 2, and then we throw that out. Okay, and it continues like that. Okay. So now let's say that let's just say that each of this is pipelined by the whole thing. Think about this carry ripple multiplication process is pipelined by a 1-bit adder. So everything is pipelined by at the level of 1-bit adder. So if I start this operation, okay, I have to go here. So I start this operation at clock cycle 0. This is A0 B0. That's when it's available, and I can start this as 1, 2, 3, etc. Because it is pipelined at 1-bit level, 1 plus 1 becomes available at 2, and this becomes available at 3. Okay, and then this result becomes available at 4, and this becomes available at 5. Okay, so then AB3 can begin at 5, and so that would be AB3, and the first, okay, so we just again we throw that away, and AB4, which is here, so that can begin, so this is 5, that's 6, that's 7, so AB4 can begin at clock cycle 7. So I'm not going to write a lot more. So this is 8, and then 9 AB5 can begin at 9. So 9 would be available at, so then AB6 can begin at 11, AB7 can begin at 13, and the final result will be available at 14, if you want to think about that. So that's 14. Okay, so that's the latency. The so-called latency, which I talked about before, is 2 times, in this case, W minus 1. In general, would be W1 plus W2 minus 2, because the word lengths are same, so that's 2 times W minus 1. Out of these 14 cycles, as you notice here, so these positions either start with the neglected bits or eliminated bits 2, 4, 6, 8, etc. Or you think about the first add positions. The first add positions are 1, 3, 5, 7, etc. So every time I have a new row to add, that introduces a latency of 2 cycles. So if I have 8 things to add, so the word length is 8 bits, 8 things to add, 8 things can be added by 7 adders. Well, 7 adders, because the first 2 are by 1 adder and then by 7 adders. So that's 2 times W minus 1. Now what would happen if I was able to take B and now replace so let's say that I have 8 bits here, and then I do sign extend by 2 positions, and we'll see in a minute why. Okay. Okay, so so if I have 4 rows to add instead of 8 rows to add, so here we had 8 rows to add, and the latency was 14. So now we have 4 rows to add. So if I start with this at 0, 1, 2, this would be available at 3, so I can add this at 5. This would be available at 6. I can start this as 8. Then the result will be available here at 9. Okay. Okay. So so why do you think that? So the latency now in this case is W minus 1, which is already there, plus 4 things to add. 4 things to add introduces latency of, so this 4 W minus 1 is 7, and 4 things to add would be by well, I guess this could be W minus 2. I guess I could take this as W minus 2. No, anyway, it doesn't matter. So so the 4 rows to add would be roughly about W by 2, which is well, it should be the number of adders is W by 2 minus 1, I guess. So we have total W by 2. So this is 3 add operations going on. So 4 things to add, W is 8, 4 things to add. So there are 3 adders, this is first, second, third, and then there is an inherent latency of let's take W minus 2. So that's 8 minus 2, so that's why that latency is 9. Okay, so what I want to point out is that if I could take the number of rows to add, so if the number of rows to add is W, so this now latency is roughly order of about 2W. Okay, so think about W to be a big number, so that's, don't bother about that constant, so that's about 2W, and this is about 3W by 2. Okay, so the main, and we'll talk about how we get to reducing the number of rows to add from 8 to 4, but what modified booth recording does is it reduces the number of rows to add from W to W by 2, and therefore reduces the latency from roughly twice the word length to 1.5 to 1.5 times the word length. So that's a 25% reduction in latency. Okay, so that's the main advantage of modified booth recording. So modified booth recording reduces the latency of the multiplication by 25%. Okay, how does it achieve that reduction? Okay, well, so A, which is in this example we had in the 8-bit example, the number A, well, it so happens that we are reducing B to 4 rows instead of A, but it doesn't matter. So we can take, well, I could take B, it doesn't, I guess it doesn't really matter. So I could take B, okay. So B is minus B7 plus B6 2 to the power minus 1 plus B5 2 to the power minus 2 plus B4 2 to the power minus 3 plus B3 plus B2 plus B1 plus B0. Okay. So that's the value of B. So B has these 8 bits. Now if I could take B 8 bits and create a 4-digit system. So here is how it works. So we append this as a 0 and take these 3 bits and we encode that to something called B0 prime. Okay, we take that and we append that becomes B0 prime. Then I take the B1 from the previous one and the next 2 we call that B1 prime. I take B3 from the previous one, group with the 2 new bits and call that B2 prime. I take B5 and with 2 new bits I call that B3 prime. That's what modified booth recording does. It encodes 3 bits to a digit. So these B primes are called digits. Okay. Now how does it encode? The process of encoding works like this. So B3 prime is equal to minus 2 B7 plus B6 plus B5. B2 prime is going to be minus 2 B5 plus B4 plus B3. B1 prime is minus 2 B3 plus B2 plus B1, and B0 prime is minus 2B1 plus B0 plus 0. Okay. All right. So, so in general, then if we have a W bit number, we take a 0 at the LSB position, we append a 0, and then we keep taking groups of 3s with one overlap from the previous digit and 2 new ones, one overlap, 2 new ones, like that. And by doing that, we can take a W bit number and create a W by 2 digit number. Now, what is each of these bits is either 0 or 1. So, B6 for example is 0 or 1. Now, what is the dynamic range of each digit? What is the dynamic range of these digits? So, if I have B, let's say B1 prime, okay. So, what is the dynamic range of these digits? So, the value of this, so each of these bits is 0 or 1. So, just plug in 0 or 1. So, the maximum value, so for example, B1 prime will be max when B3 is 0 and B1 equal to B2 equal to 1, and that means maximum value is 2. Minimum will be minus 2, because when B3 is 1 and B1 equal to B2 equal to 0, so the minimum is minus 2. So, each of these digits is taking 5 possible values: minus 2, minus 1, 0, 1, 2. So, instead of, so when I talk about this modified Booth recording multiplication table here, each of this value here is taking values, 5 possible values: minus 2, minus 1, 0, 1, and 2. Okay, so let's just try to prove that that indeed the value of the digit has not changed. So now we define. So think of these. So this weight now is 2 to the power minus 1, 2 to the power minus 3. So think of this as point. So radix point here, and then these values 2 to the power minus 5, 2 to the power minus 7. So so B is equal to B3 times 2 to the power minus 1, B3 prime, plus B2 prime times 2 to the power minus 3, plus B1 prime times 2 to the power minus 5, plus B0 prime times 2 to the power minus 7. Okay, so if I take that and substitute these values, so that's minus 2 B7 plus B6 plus B5 times 2 to the power minus 1, plus minus 2 B5 plus B4 plus B3 times 2 to the power minus 3, plus minus 2 B3 plus B2 plus B1 times 2 to the power minus 5, plus minus 2 B1 plus B0 times 2 to the power minus 7. Okay, so so that's the value, that's of the recoded number, and let's just try to match these coefficients and see if indeed B represented by this binary bit and the modified Booth recorded digits, are they indeed the same number or not. So let's try to check. So is B0, B0 has weight 2 to the power minus 7. What's the weight of B0 here? 2 to the power minus 7. What's the weight of B1? 2 to the power minus 6. Now if I collect all B1s together, what is going to be the weight of B1? So weight of B1 is going to be minus 2 times 2 to the power minus 7 plus 2 to the power minus 5. Okay, so minus 2 to the power 6 plus 2 to the power minus 5, which is equal to 2 to the power minus, we want minus 6. So if I take 2 to the power minus 5 taken outside a bracket, and then 1 minus half, 2 to the power minus 1 is half, which is 2 to the power minus 5 times half, which is 2 to the power minus 6. And you can take any of this. So B2 has no overlap, so that's B2 times 2 to the power minus 5, B2 times has no overlap. B3 is an overlap term that has overlap here, and you can indeed do the same thing and show that B3 has weight 2 to the power minus 4. Okay. So that's really 2 to the power minus 3 minus half of 2 to the power minus 3, and that's how we get 2 to the power minus 4. So now we can, by these equations, we can verify that the modified both recorded encoding, some people call it decoding, but is indeed not changing the value of B. Okay. So now you can relate back to what I was saying. So now if I take an 8-bit value of B and then replace that by 4 digits, and then I can replace by 4 rows. So I can get to these kinds of 4 rows by again by A times B can be written as A times B3 prime times 2 to the power minus 1 plus A times B2 prime times 2 to the power minus 3 plus A times B1 prime 2 to the power minus 5 plus A times B0 prime 2 to the power minus 7. And if I by the way, it may be a good thing to check the last value. So the last value is minus 2 B7 times half minus B7, that matches. And so if I again apply the Horner's rule, so this would be A times B0 prime times 2 to the power minus 2 plus A times B1 prime, and that whole thing again apply Horner's rule. So this is 2 to the power minus 5, and that's 2 to the power minus 3. So if I take 2 to the power, so this would be 2 to the power minus 3 taken outside a bracket, A B2 prime plus 2 to the power minus 2 times that, and then from 2 to the power minus 1 and 2 to the power minus 3 I can take 2 to the power minus 1 outside a bracket, and then we have A B3 prime plus that whole thing. And that's okay. I can see why I was a bit confused, but I can see why I was being confused. Okay. So okay, so now you can see that A B0 prime times 2 to the power minus 2, that's a scalar by 2 to the power minus 2, that's like dividing by 4, throw 2 bits out. So throw 2 bits out and sign extend 2 bits. So that's really A times B0 prime times 2 to the power minus 2. Okay. Then this is A times B1 prime. Okay, so finally, okay, I was being a little confused here because finally what I forgot to do, which is I need that 2 to the power minus 1, and therefore this must be thrown out, and there has to be another sign extension, and the first result really will be available at 10, which is W minus 1, and I was trying to see. So this should be 7 plus 3, which is 10. Okay, so that should be, that's actually the correct result. It should be 3W by 2, 3W by 2 minus 2. So that's the correct result. So 2W minus 2 replaced by 3W by 2 minus 2 minus 2, which is same as, yeah, that's. So I was wondering why I was getting 9 but not 10, and now I see that we forgot that 2 to the power minus 1, so I have to throw this away and sign extend, and the first bit will be available at 10. Okay. Well, how many of you have seen this before and have gone through in a class before? Anyone? I thought that when I taught this class before, the students would tell me they have learnt this in one of the VLSI design classes, probably VLSI design 2. Does VLSI design 2 teach any of these things? We used to teach this maybe 10, 15 years ago. So, but that's good that they are not teaching, because you are in this class and you can learn some essence of arithmetic is very critical. So, the book again doesn't really get into a lot of detail, but it does give you enough hints. It does give you enough hints to tell you how to design both decoded multipliers. So, so we won't go into, and usually students do these things as homework, but I'm not assigning homeworks. But at least if you want to, well, of course, you can always Google these, and there are papers and so on. So, so there is so the problems 4 and 5 ask you to prove Baguli multiplication. Problem 11 asks you to, it gives you enough steps to design finally the how to first design the circuits for modified booth recording, and it gives you the answer, and it just asks you to get those logic. You can do some Carnot map minimization. I think the table is given here, so you can do some Carnot map, and then there's more continuation of that booth. So this problem 11 and 12 talk about designing modified booth recorded multipliers. Okay, great. So we have seen that by recoding bits to digits, we can reduce the latency by 25%, and that's great. That's certainly great. That's a very good way to reduce latency. So as you can imagine, the so let me see if I cite a reference. So the Baguli citation is here. That's Transactions in Computers in 1973. Okay. Okay, I think I didn't cite the booth paper, but I think basically it gives you some books on computer arithmetic. But I will talk about the Wallace tree right away. So that's what I want to talk about next. Okay. Okay. Well, so there is a little history that I was going to see if there are papers that I could point out. But the reason it's called modified booth recording. So the so-called booth recording was useless. Okay, the booth came up with this idea, what is booth recording, and that was really not useful at all in reducing the latencies. Okay, so the original booth algorithm says this. So if I have 8 bits, and then we append a 0, let's say, and then we take these two and recode that to something, take these two and take these two. So what was happening, we start with 8 bits and we still have 8 bits. We were now recoding 2 bits to this digit. And so if you think about, let's say this is B0 and B1, and we recode that to B0, well, this would probably be B0 prime. So I recode that to B1 prime, which would be minus 2B1 plus B0. If I take, I'm not quite sure if that was the formula or not, but even if I do take that to be the formula, then this would be minus, yeah, I'm not quite sure what the original booth recording formula was. But here is the thing, if you take 8 bits and you get back 8 bits, there is no reduction in latency. So the modified booth recording uses this essence of booth recording, and let me see if we have any reference in Appendix E that I could 0.2 maybe not. So yeah, but so you can do some Google search and find out. So so the original booth recording was of no use, but the modified booth recording says, okay, we can now append 0, but instead of grouping with 1 bit, so group with 2 bits. So that's, so take this and group with 2 bits, and take this and group with 2 bits, and that's why the W rows are reduced to W by 2 rows. This W rows is still reduced to W rows. So the original booth recording was really of no practical use, but the modified, it's called modified because somebody, I don't have the right reference, but some other paper took the idea from booth and modified that it's useful. Okay, that's great. So modified booth recording is part of every microprocessor, every multiplier out there on this in the semiconductor market. Okay, so but okay, we have now these modified booth recorded partial product rows to add. That's great. Yeah, that's great. But so, but this essence of what I showed, which is adding these still adding these in this manner, either in carry ripple or you could save the carry. So instead of rippling the carry, so the carry is generated here, and in carry ripple you move that to the left, and that becomes part of this add. What is carry save doing? Carry save says, well, it's still part of that result, this whole result, but don't ripple to the left, save it and put it here. It's still being part of that partial part of that final result here, but put that here, save it and add it to the next row. That's what. So it doesn't matter whether we add, ripple or save, we still have these many things to add. 8 things can be added by 4 things still can be added with that latency. The latency increase is not going to change. It's not going to change. So so there are many ideas of reducing the latency further, and we can do that by binary tree or by Wallace tree. So every time you hear about what the multiplier is in the microprocessor or in products, so there are lots of, we talked about tree adders. Okay, well, what does a tree really do? So if I'm adding a plus b plus c plus d, so you take a, add that to b, add that to c, add that to d. I mean, that's kind of what is known as a linear adder, linear or sequential, sometimes called linear tree. Okay, I mean, that's just linear. No, it's not a tree, but it's a linear tree. Okay. A binary tree, you take a and b and add them, and take c and d and add them and add these two, and then we get the result. So in case of add, the latency is reduced from w minus 1 to log w to base 2. So if I have 128 things to add in a linear tree, the latency would be 127. And if I have 128 things to add, I can do that in log 128 to base 2 or 7 steps. So that's the latency 7. Okay, so and people who are doing that. So in case of digital filters, we talked about all these digital filters. So where we take this. So in the beginning, okay, long ago, now not anymore, but long ago, people used to take these direct form FIR filters, and then instead of adding them in linear adder, or they were adding them into logarithmic process. So 4 things here can be added by 2 steps as opposed to 3 steps. So people used to do that, and then of course people used transpose structures and hybrid structures and so on. And the advantage of transpose and hybrid, that we did not need to go through this. So we didn't really need all these tree configurations anymore. Okay, but in case of applying the same idea, so same idea, we are applying the same idea, so we can design binary tree multipliers, and there is also something known as a data multipliers. Professor Luigi Dada of Milano, Politecnico di Milano in Italy. He has passed away, but the so-called data multiplier, that's kind of has been existing for a long time, but that is no regularity, so that's why people use Wallace tree, which is more regular. Okay, so what are the essential ideas in tree multi? What does a binary tree do? So the same process of divide and conquer. So you take a large problem and divide it to two smaller size problems. So if I take that number b that I talked about, that we just saw, so that number, well, the beginning number b. So let's take, I mean, I could take b prime too, but if I took that beginning number b, and I could write b as, so as b high plus 2 to power minus 4 times b low. Okay, so think about b low constitutes the bits b3, b2, b1, b0. So that value would be b0, so b3 plus 2 to power minus 1, b2 plus 2 to power minus 2, b1 plus 2 to power minus 3, b0, and that times 2 to power minus 4 would be the second part, and the first part, which is b high, would constitute the bits b7, b6, b5, b4, and that would have this value. So b, you can think about these bits. So here this is a signed bit, and you can think about b low to be unsigned. So these are all unsigned. Okay, so you can have signed multiplier or unsigned multiplier. Now a times b has now been broken down into two multiplications. So I can multiply by ABH, the high part, ABL, and then finally add them together by the scaling operation here. And so if B was, let's say, 32 bits, I can describe that as a 216-bit multiplier. So if B is 32-bit originally, so this is, I don't know what the word length of A is, but this is multiplied by 16 bits, and then I can decompose that to 8 bits and then to 4 bits, and that's the essence of divide and conquer. So that's what is binary tree. Binary tree means you take a big problem and divide that into two small problems. Okay, so binary tree indeed can then reduce the latency in a logarithmic manner to base 2, log to base 2. That's the reduction in just as the FFT does. So instead of W, so the W that I was talking about, that W, which is so this was 2W minus 1, because it was W minus 1 because of the sequential add, and another W minus 1 because of the number of rows being W. So that's why. So this is due to the number of rows, and this is because of the sequential add process. Now if I replace that sequential to binary, that becomes log W instead of W minus 1, exactly as I showed you in just adding. Latency is reduced from w minus 1 to log w. Okay. So that w minus 1 part of the sequential multiplier, and that part is reduced to log w. So in fact, so you can see that if we used binary tree plus booth recording or modified booth recording, then the total latency would be essentially log w2 plus base 2 plus w by 2 minus 1. So this is due to the tree part, and that's due to the recording part. Okay, so that gives you an idea how these latencies of multipliers are computed. Okay. Okay, so so what are other ways of computing? What are other ways of what's the difference between data tree and Wallace tree? So Wallace tree, as you will see, instead of reducing that to log to base 2, it reduces to log of w to base 3 by 2. Because at each step of the divide and conquer, we take 3 rows and reduce them to 2 rows. That's why, and then you keep repeating that process. So that's why it's a logarithmic with respect to base 3 by 2. Okay, so let's go to appendix E, and I don't really want to go through these in great detail, but at least I can walk you through what it does, and you get a sense. Okay, so so this is an example of 8 by 8 data multiplier. Okay. So do you recognize, are you able to recognize this as the all the partial product bits organized for 8 by 8 bit multiplier in this manner? Are you able to recognize that or not? Okay, let's take an example. So if let's say that I had, let's just for now think about unsigned, and let's not worry about sign extension and all those things. So let's say that I had a 4 by 4 multiplier, something like that. How many of you can see that these two are same things? Raise your hand. How many of you see these two are same things? What is at every dot? At every dot there is some A, I, B, J, right? At every dot there is some A, I, B. So how many of you see that these are same things? Okay, how many dots are in this first position of this? So 4 by 4 will have 7 bit result. So how many are in this one? Okay, how many are here? 2, 2. How many are here? 3, 3. How many are here? 4, 4. 3, 3. 2, 2. 1, 1. So now can you see what we are doing? We are taking this dot, pushing that to the bottom. These 2 from top 2 lines, push to bottom 2 lines. These 3 pushed 1 down. 4 stage it is, 3 stage. Okay, these stages. Do you now see that these are same? Okay, good, good. So now what Dada's idea is very simple. I mean, a very clever idea. So so that's what we begin with. So 8 by 8 multiplier, and it looks like a triangle. So you can have a parallelogram. So you have a 8 by 8 parallelogram looking like that. Rearrange them to look like a triangle. Okay, that's the starting point. Okay, so that's called stage 1. And what do you think is going on here? So the idea of the data's basic idea is, whichever, think about this as a big triangle, what we are interested in doing is push its depth down. We want to reduce the depth. So push it down, whichever is the tallest. So think about, well, think about, you have, let's say that you have certain sticks, these are sticks, and let's say these are not hard sticks, you could compress them. So if these are sticks, whichever is the tallest stick, you push it down, so then that matches with the next tallest. So that's kind of the idea. Okay, so so the tallest part here is the middle part of the triangle, right? So that if you look at in the middle part, so what is the height of that middle part? 3 plus 2 plus 3, 8. Okay, so the height of that is 8. Okay. All right. So so as you can see here, so what it is showing here, so the height of this is 8, and if you think about what is the height of, well, as you can see that we don't any longer have something with height, the highest height now is 6, and that's 6 here, 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 here. So now I now have 5 instead of having, so this was 8, this was 7, this was 6. So we have pushed down essentially the first two rows, which had height 8 and 7 have now disappeared, and now we have height 6. So height 6 is now for these 6 of these columns. 6 columns have height 6. Okay. So how do we get height 6? How do we get height 6? All right. So this is how it works. So these groups that are shown here, those groups are so there are 2 things here and 3 things here, and those are added. So that's what is being done here. We add these 3 things, so we can add 3 things by a full adder. And a full adder, so if I add these 3 things by a full adder, what would happen to that? What would happen to that? So if I add, so let's just I add 3 things, a plus b plus c, it generates a sum and a carry. So every time I replace these 3, so something that looks like this is really generating that. So it's generating a new dot in the same column and a dot in the column to the left. Okay, so now, and half adder, same thing. If I have a plus b, generates a sum and a carry. So sum is here, carry is here, so generate something like that. Okay. So whenever you see these compressors, so this is a binary adder, a full adder. You can think of a full adder as a 3 to 2 compressor. So it's compressing 3 bits to 2 bits, and a half adder is a 2 to 2 compressor. Okay, it's taking 2 and still creating 2. Okay, so now, so what exactly do you think happened from first stage to second stage? So take these 3, replace by 1 dot in this column and another to the column to the left. Take these two, keep one dot in this column and take another to the left. Now out of these 8 dots, how many dots do we have in this column now? In the middle column we have 6. Why? We have 3, we got 1 because of these 2 dots, 1 because of these 3 dots, and 1 to the right half adder that generated 1 carry to the left. So we now have 6 dots. So the first stage of compression really involves these circles. Okay, we have these circles here, so we are trying to push down the height. That's the essential idea, push down the height. The height was 8, now push down to 6. Okay, so so just do these compressors and that's what you get. And then we do these operations here. So we take these 3 and create a sum and a carry, sum and a carry. So what do you think is happening? So let's take okay, so let's see what's going on here. So I take let's see, 1, first column stays the same, second column stays the same, third column stays the same, fourth column stays the same. Okay, so these have stayed the same. Fifth column, the depth was 5. What's the new depth? Fifth column new depth is 4, because that 2 in circle becomes a half adder as a sum and a carry. So now new depth is 4. Now what is the new depth of the next column to the left? So 1, this becomes 1 dot and another dot carry from the right hand. So that becomes again 4, and this becomes 2 dots and 2 to the right circle come 2 more carries, that becomes 4, and so on. So again the height, think about the height, we are pushing down the height. So the height was 6, now height is 4, then do these circles, then height becomes 3, finally these add these things to by full adders, then you get 2, and these are 2 vectors. We can think of them as a sum vector and a carry vector, and then you can have vector merging add operation. So that's the 8 by 8 bit data multiplier. Nobody uses data multiplier. The idea is certainly great. Nobody uses data multiplier because where we are putting these circles ultimately is very irregular, and there is no direct formula. So data, I had the very privilege of meeting Professor Dada at one of the conferences, but as you can imagine, he was already too old by then and was really not able to walk, and he was helped by his wife who was working with him all the time. So, but that was I can't remember, long ago, maybe 20 plus years ago. So that was the Data Multiplier, published in 1965. So the Wallace tree, which is 1964. Let's talk about what the Wallace. So now that you understand the basic idea of the compression or reducing height step, so this is an example of Wallace tree for a 4 by 4 bit multiplier. Okay, so so these are the parallelograms. Now we don't put them into triangles. These are the parallelograms here, and the first step, first stage is take. Okay, so you see here. So take the first. So how many lines are here? 4 lines. How many lines do you see in the next one? 3 lines. Why? So essentially what we are doing is taking, so out of the 4 lines, take 3 lines and add at every position, use a full adder or half adder as necessary, and create a sum and a carry. So 1 stays as 1, 2 added by half adder is a sum and carry. These are one group. Next one 3 added by full adder, sum and carry. Next 3 sum and carry. The last row is sitting as it is. Okay. So now every 3. So now every column that has 3, I can now create sum and carry. and then this is just a vector merging add because now we have two vectors to add. So that's illustrating the simple case of Wallace tree for 4 by 4 multipliers. Okay, what happens if it is 8 by 8? So now we have 8 rows to add. So we are now having 8 rows to add. So we don't need to convert these to triangles. So here is how that works. Take first 3 rows, okay, and replace first 3 rows each position by a sum and a carry like that. So first 3 positions create 2 lines, 3 lines create 2 lines. Next 3 rows do same thing, next 3 rows create 2 rows. Leave the last 2 as it is. Okay. You can't reduce them anymore anyway, so leave them as it is. Now how many rows are here? So if you count 1, 2, 3, 4, 5, 6. So 8 rows have been now changed to 6 rows. Okay, 8 to 6. Okay. Okay, so 8 has been, so think about the general process. If I had 9 rows, how many rows would be here if I had 9 rows? Every 3 replaced by 2. How many 3s are in 9? 3 3s, and each 3 creates 2, so 3 times 2 6. So whether it is 8 or 9, it doesn't matter. If I had 12 rows, that would be 4 groups of 3s, we would have 8 rows. So every time you have certain number of rows. How many rows do you get in the next step? Multiply by 2 by 3. 3 replaced by 2. So if we had 15 rows, that would become 15 times 2 by 3, which is 10 rows. 10 becomes 10 times 2, 20 by 3. That becomes 7 rows. 6 point something, you take the next integer. So that's why 3 becoming 2 and keep going. That's why the logarithm base is 3 by 2. Okay, here 6 becomes 4. Take 3 rows, becomes 2. Bottom 3 becomes 2. Now 4 becomes, out of the 4, take 3 rows, becomes 2. The last one as it is, and now we have 3 becomes 2. Then you do the vector merging. Okay. So anytime you see a microprocessor or anytime you see a multiplier in some GPU or CPU or whatever. So all of those for many decades have been using Wallace tree and modified Booth recording. Is that clear? Okay, so at least we have gone through the principles of Wallace tree and modified Booth recording multipliers. Any questions so far? Okay, I am now going to talk about one of the designs that was very popular in 60s. In 60s, okay. Well, I mean, that's kind of, as you can imagine, in 1960s with discrete components. Okay, let me tell you that some of the original second order biquad filters at MIT Lincoln Labs were implemented using discrete components and were very bulky. Okay. So in those days, as you can imagine, I mean, algorithms like the fast Fourier transform that came along because the CPUs, the IBM computers, had shift and add. So multiplication was computed by shift and add. So as long as we can reduce the number of multiplications, then we can reduce the number of cycles, and that led to a number of fast algorithms, and one being the fast Fourier transform. Okay, people implementing these not in IBM computers, but by application-specific computers using whatever components they had in those days, maybe vacuum tubes, maybe something else, I don't know, but using parts that were available then. So one way to implement these using less parts, less circuits, is instead of implementing parallel multipliers, people who were implementing bit serial multipliers. And there was at Bell Labs, and primarily at Bell Labs, in those days there was a lot of interest in bit serial digital filters. So a lot of the digital filters that we have talked about in the class were implemented using bit serial arithmetic. And what does bit serial arithmetic do? Well, it says that if the word length, let's say I want to implement a digital filter, yn is equal to minus 11 by 16. Let's say yn is equal to xn minus 11 by 16 xn minus 1 plus 3 by 32 xn minus 2, something like that. And that kind of filter, well, let's say the word length was 16 bits, and in that case we would input the input x in bit by bit. So this is a bit serial filter, and that would compute the output bit by bit. So this would be 1 x, let's say xn, the next 16 would be xn plus 1, and so on. So in bit serial digital filters, the signal is processed 1 bit at a time, and as you can imagine that bit serial, the whole parallel multiplier, the total, because of the parallelogram or the triangle, it doesn't matter. So if you think about a parallelogram of size w by w, there are w squared dots sitting there, which are partial products. So in general, the total number of adders is roughly proportional to w squared. In bit serial, these are about w, well, about w. So the bit serial multiplier can be computed by using about w binary adders as opposed to w squared. Okay. 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 How does a bit serial multiplier work? So I can go back to the original a times b. So if I go back to a times b, which was we had this equation here, minus a times b 7 plus 2 to the power minus 1 times a to the power a b 6 plus 2 to the power minus 1 times a b 5 plus 2 to the power minus 1 times a b 4 plus 2 to the power minus 1 times anyway, close 6 brackets. Okay, close 6 brackets. All right. So so now I initially I was writing down these one by one, as you can see that. But now think about. So we are adding. So let's go back to just one of these. So a b 0 is a 0 b 0, a 1 b 0, a 2 b 0, a 3 b 0, a 4 b 0, a 5 b 0, a 6 and a 7. Okay, so that's a times b 0, and times 2 to the power minus 1 is going to throw that out and sign extend a 7 b 0. And we will add to that a b 1. So a 7 b 1 through a 0 b 1. So that's what is going on in the fast adder, beginning adder. So so let's say that we had a coming in so a comes in serially. A0 is available in clock cycle 0, A1 is available in clock cycle 1, A2 is available in clock cycle 3, etc. Okay, so so what this says here, so I take this line A, so A is coming sequentially, and then we take the partial product with respect to bit B0. So now I have computed A times B0. The next step involves multiplying this. So we'll talk more about that, but in terms of a high level block diagram, so AB0 times 2 to the power minus 1, we'll talk about that, what that means, plus A times B1, so add these, multiply by 2 to the power minus 1, plus AB2, add these, so we are now showing a sequential. We are now showing a sequential adder. This is a minus sign because we have to do minus AB7, so that's a subtract, and that's the product A times B. Okay, whichever it is, X or whatever. Okay, so that's a high level view of this bit serial multiplier. So now we have W minus 1 AND gates and W minus 1 adders. Okay, W AND gates. So we have W AND gates to generate the partial products, W minus 1 adders, binary adders, and these W minus 1 scalars. Now what does really a scalar do? What is the purpose of a scalar? The scalar is an important element because what it does, it throws the ALSB out and then sign extends the MSB. So if I have a number A, okay, and I want to compute A times 2 to the power minus 1. So this is now coming serially, A0, A1, A2, etc. So what does this really do? By the way, let me tell you that so if I have A0, A1 up to A7, and then the output is going to be what? We throw this out, A1, A2 up to A7, A6, A7, and then A7. So these were input in clock cycle 0. So when was A1 input? Clock cycle 1. I want A1 in what? Clock cycle 0. So multiplication by 2 to the power minus 1 is a non-causal operation. It cannot be implemented because A1 is input at clock cycle 1 but is desired at clock cycle 0. How do you solve these kinds of problems? You make them causal. How do you make it causal? You introduce a latency, and you have gone through some of those things. So introduce 1 unit latency, and that means what we can implement is really 2 to the power minus 1 followed by a delay. So 2 to the power minus 1 followed by a delay. So a delay is introducing 1 unit of latency, or that makes it causal, and so now that is implementable because if I have a delay of 1 unit, then this is no longer 0. 0 plus 1 is 1, and then that's 2, and then you can see it was in 2. So now you can see that this whole thing is nothing but a multiplexer such that the switch is every time here, but in clock cycle W times L. So for example, if word length is 8, then this would be 8 times L. So what does that mean? It means that in clock cycle 8, so A0 is fed in clock cycle 0, A7 is fed in clock cycle 7, A8 is fed in clock cycle 8, A9 is fed in clock cycle 9. So in clock cycle 8, when the input is A8, the switch is connecting here. And what does that mean? It's feeding the output of the delay. What is the output of delay? So whatever was fed here in clock cycle 7 is available here, and in clock cycle 7 we had A7. So A7 was here in clock cycle 7, comes here at clock cycle 8, and that is a sign extending the A7. And at same time, because the switch is never pointed here, whatever came in clock cycle 8 A8 is never even fed to the output. So this switch, or the 2 to power minus 1 followed by the delay, is killing two birds in one shot. It's eliminating the LSB and is a sign extending the MSB at same time. So we'll stop here. We'll continue with bit serial digital filters next time. Okay, those of you who are here, your graded homework is here, so don't go away. Come.